So in section 3.1, we discussed the mean and measures of central tendency. To find the average or mean of something, we would add it all up and then divide by n. So if you divide 365 by 5, you'll get, say, x bar equals 73. And interestingly enough, if I do that for this other team, I'm assuming that these are the heights of a starting 5 players on a basketball team, maybe a high school team. We also get 365, so the sample mean here, regarding these as samples, would also be 73. So, wow, is that all there is to say here? These two data sets are essentially kind of the same? Or is there some aspect of the data that looks different? Now, I have graphed these. So team 1 is in pink, that's above the line. Team 2 is in orange, that's below the line. Are these data sets more or less the same because they have the same average? Or is there some aspect of the data that, you know, just the average doesn't really capture?
One is more spread out, so that's why it's...
Nice. One is more spread out. So one way you can measure how spread out something is to look at the range. So the range of the data set, what do you think a good way to measure the range or how spread out the data is? What's a first pass at this?
Maximum and minimum?
Yeah, perfect. Take the max minus the min. And that's going to be our range. So we can look at the range for both of these data sets. So in this one, say the range, well, that's just top minus bottom. That's going to be a range of 5. How about the range of this one? It's okay if you take out your calculators.
12.
Thank you. Range is 12 on that one. All right, so that's not bad. The problem with just using the range is that it only incorporates 2 numbers out of this whole data set. Anything underneath here could be going on, and we wouldn't really know it. So it'd be nice if we had a little bit more comprehensive measure of just how much spread there is in the data. And so I'm going to try and build one from scratch here. Now, if you want to follow me along on your Google Sheet, that's great. If not, that's okay too. But we want to find out how spread out the data is. So what I propose to start with is I'll take these numbers, so my x values, and I'll subtract off the mean. So I'll do equals, and then I'll click this cell right next to it, and I'll subtract from that 73. So that first one's going to look like B3 minus 73. When you hit enter, at least on my sheet, it says, hey, want to do the same thing for the rest of these? Sure. Let's click yes. So that's how spread out each of these are individually, but you know, I want an overall measure. So how about if I sum up those values here? So I'll do equals and then sum and add up all those. So you can click, drag, and highlight, and it'll be the sum of C3 to C7. And that's going to be a measure of how spread out the data is. Except I get a 0. That's not very good. 0 is telling me about that much. It's telling me nothing. Let's take a look at our second data set. Well, let's see. I'll just do it kind of quick here. You don't have to necessarily follow along. I'm going to see if that happens over here as well. So equals this minus the same mean, which is 73. Yeah, fill it all up. And let's add all these up again. And guess what? Same thing happens. In fact, no matter how often you do it and what data set you use, if you subtract the mean and then add up all those differences between your data and the mean, you're always going to get 0. So as far as a measure of how spread out the data is, just subtracting the mean and adding things up doesn't work good. So here's what we'll do. The problem is that we got all these negative signs. So one way to get rid of those negative signs is to square everything. Equals. So hit the equals, click this cell, and shift 2. So you're going to square that number. So instead of the deviation which is really the distance between that and the mean, we're going to get the squared deviation. And kind of like the last one, they asked, do you want to do this all the way down? Sure. And then as before, we did our total. So let's get rid of that. This is going to be the total now, equals, am I going to get 0 if I add this up again? No, clearly not. Everything's positive or 0, so I'm going to get something above that. And I get 14. Now what you've calculated so far is just this much. You've calculated the sum of the x's minus x bar squared. That's what you've calculated so far, if you wanted to keep up with that. There's a problem. If I add more and more values to the data set, this sum is just going to get bigger and bigger and bigger. And it's not going to be necessarily a good reflection of just how much spread there is in the data. So what I'll do is I'll try and calculate kind of an average. Now when you calculate an average, like over here, when I got my total 365, what did I divide by to get the average? 5. So you're dividing by n, where n is the number of pieces of data in your data set. I'm going to do similar over here, but instead of dividing by n, I'm going to divide by n minus 1. And that's going to give me something called the variance. So that's going to be our s squared. So in our case, here, I'm going to take this and divide by 4. So if you want to, you can click this, click equals, D9 divided by 4 should give you 3.5, and that's what's called your variance. So let me just write that in here next to it. Sample variance, variance. And that's not bad. There's just one problem with this that we don't like. If you're keeping track of the units, and these are really the heights of basketball team, that's in inches, but this would be in squared inches. And squared inches doesn't really reflect height too much. Squared inches is something you associate with area. So it'd be nice to get back to the original units. So if I have something which is squared, what's the way to unsquare? What's the fancy word we use there? Square rooted. So let's take the square root of this, equals SQRT, and then click that cell. Square root of this, and that finally brings us to what's called the sample standard deviation. And that's what we're looking for. Now, if you didn't quite follow all the calculations and the wheres and why-fors in between, that's not a big deal here. I'm not going to ask you to calculate the standard deviation by hand, all right? We've got a ton of technology that'll do that stuff for us. What I want you to know is what the standard deviation is, what it measures, how it changes, this, that, and the other. So here's the standard deviation. Okay, that's a good measure of how spread out things are. If you're to follow along to the Desmos link that I provided online, you can see a little data set there that you can kind of play around with. And so you can move these values around. So you can see that it adjusts the maximum height, or moving this affects the mean. But watch the effect of things on the standard deviation. So if I move this up, my standard deviation over here, starts to decrease a little bit. I can move some other things out here, here, and here. Standard deviation starts to increase a little bit, and then it starts to increase a lot. So, standard deviation overall is starting to measure how spread out the data is. And you can see that in playing around with things. Let's go to another extreme here. So most of the data here is along a straight line. Take a look at the standard deviation. Kind of small compared to the previous example, right? Over here we had a standard deviation over 5. Here we've got something less than around 0.05. What do you think the smallest value for the standard deviation could be? What would you guess? 0. Yeah. Let's take a look back at our data set here. Like I said, we're not going to worry about calculating standard deviation by hand. All right, you can do the same kind of stuff for this data set that we did here. But which data set do you think for team 1 or team 2 is going to have a larger standard deviation? Should be team 2. If our standard deviation is doing what we think it's supposed to, then it should measure how spread out the data is from the mean. And the bigger the spread, the larger the standard deviation should be. So let's just kind of cut to the chase with this. I'm not going to go through all that painful stuff that we did just a moment ago. If you caught on to it, great. If not, catch on to this. Equals STDEV. And you can hit the tab key once it starts to recognize that. I want the standard deviation of these 5 numbers. So click and drag over that. Put a right parentheses if you feel like it. Oh, 5.24. So, all right, what it's saying is that the standard deviation here is bigger than the standard deviation here. It's a lot bigger, right? Almost 3 times as much. But that reflects that you've got more variability in the data for team 1 than you see on team 2. Now you can see that visually here. This is much more spread out than this. So, great. All right, I want you to make a prediction here. Are we okay with standard deviation so far? Let's scroll over to team 3, which I'll affectionately call team clone. And here's the heights of team clone. So, I want you to make a prediction. What do you think, if I do the standard deviation, what do you think the standard deviation of that data set is going to be?
0.
0. Well, why don't you find out? Equals standard deviation. Click and drag over that data set, and your prediction is exactly right. Standard deviation is 0. That's as small as it can get. What it's literally saying is that there's no spread in your data, right? It's 0. There's no variability in that data set. That's the only time you're going to get 0 for a standard deviation. You cannot get anything negative. It just won't happen with standard deviation. So let's summarize a couple things about standard deviation before we move on and tackle some problems here. So the first thing that I want to nail or mention is some notation. Let me do it maybe here. So let's see, notation. So we'll have sample data or population data. And if you have sample data, then we can have a variance or we can have a standard deviation. Now our sample standard deviation is going to be denoted with an S, which is nice because it's, you know, the first letter in the standard deviation. That's great. But you might remember how we went from variance to standard deviation. We took the square root of this to get this. To go the other way, to go from standard deviation to variance, what do you think I need to do to get from here to here? Yeah, I need to square it. And in a similar way, when you have population data, and when you're dealing with population data, you have to conduct a census. You have to talk to everybody or collect data from everything in your population. If you have population standard deviation, that's going to be denoted with a sigma. Population variance is going to be denoted with sigma squared. It's not a huge deal right now, although the formula for one is a little bit different than the formula for the other. But later on, you are going to have to know the difference between these notations and when it's appropriate to use which one. As far as the summary is concerned, I would start out with this way. Summary. So the standard deviation shows the average spread of the data from the mean. Okay. And if I put on a test a question kind of like, a friend of yours knows that you're taking statistics from a handsome athletic mathematics instructor, she asked you to tell you, what does standard deviation mean? If you gave me this much, that would give you 2 points out of 4. What more could we add to try and get some more points here? What else could I add there?
It's relation to variance.
All right, it's related to the variance. Standard deviation is the square root of the variance. That's a good one. So, as far as helping your friend understand what standard deviation measures, what does it tell you? What could you say?
The larger a standard deviation, the more spread out everything is. The smaller
Perfect.
standard deviation, closer everything is.
Excellent. So, as the spread of the data increases, so does the standard deviation. And you could go on and say, you know, smaller spread, smaller standard deviation, that's fine. All right, now we're getting into the bonus part. Is there one last little thing we can add here to earn an extra point? Maybe a point of extra credit here. What one last thing can you tell me about the standard deviation that we covered here so far?
It can't be negative.
Can't be negative, all right?
It can only be 0 if there's nothing.
Perfect. So standard deviation is 0 when all the data are the same. And it's positive otherwise. That's a very complete answer. Your friend is indebted to you. All right. So let's play around with some data and try and, you know, really start to appreciate what standard deviation tells us about a data set, because the mean, the median, the mode doesn't tell us everything. So let's take a look at some of the examples. So let's see, let me make this a little bit bigger here on our screen. So we've got 2 different data sets, systolic blood pressure and diastolic blood pressure. Says these values are measured in millimeters of mercury, matched to 10 subjects, taken at random from the data set that goes with the book. Now, fortunately, that data has been typed in for you in example B, so click that down here. And here are your numbers. You know, if you wanted to, you could copy these over here, something like that. But it's not a bad idea if you can to sort your data, and that's what I've done with these values over here. A first glance at how much variability is in the data set is provided by the range. What's the range for the systolic? What's the range for the diastolic? Tell you what, I'll do the systolic if you do the diastolic. Dallas, what's the range for the diastolic be here? Or how would I find that if the numbers are eluding you at the moment?
You take the maximum, subtract by the minimum.
Yeah. Now, if I didn't feel like working too hard, what I could do is I could do equals max of my data set and copy these values minus the min of that same section of numbers. That should give me 38. Okay, so the range of that one. You can do the same thing for the range of this one. I can just copy this cell by grabbing that little circle on the bottom right and dragging it to the left. That gives me the range of my other data set. So great. So it looks like the systolic has a greater variability than the diastolic, but keep in mind that these values are based on just the two numbers. So to get a more comprehensive look at this, let's do the standard deviation. Equals standard deviation, and I'll click all those values here, 19.5, and let's see, what do you think? Am I going to get something smaller or larger when I do this systolic or diastolic? Smaller. Let's just copy that formula over to here, and bam, 12.8. So we do get something smaller, which matches our expectations. So cool. All right, how are we looking on that one? Doing okay? It kind of matched our expectations, so pretty good on that one. Let's move down to example C, which I kind of find amusing. Geography majors. The data listed below are estimated incomes in dollars of students who graduated from the University of North Carolina, UNC, after majoring in geography. The data are based on graduates from the year 1984, and the income of basketball superstar Michael Jordan, a 1984 UNC graduate in geography, is included. Does his income have much effect on the results? Well, let's see. So that's one of the data sets you have here. If you click example C, you've got two data sets, one with, one without Michael Jordan. Now, first things first, let's calculate the average or the mean here. Do you think his salary might influence the average a little bit? Think so? Let's find out. So equals average, and look, it's even suggesting what I might want. So I'll just click the tab key and say, yeah, there you go. So how about that? The average UNC graduate in 1984 was making on average $260,000. Sounds pretty good. I missed my calling, right? All right. Let's see what happens if I drag that over to here. And I don't want that middle one, but there you go. Does that average look as good without Michael Jordan in there to pump it up a little bit? Probably not. All right. Let's do the same thing for standard deviation. Equals standard deviation. And bam. So we have the standard deviation there. I don't want it to repeat that calculation. What do you think? Does standard deviation without Michael Jordan, do you think it's going to be as big?
No.
No. So equals standard deviation. And let's click these guys right up here. And bam. Significantly less. Now there's two ways you can do the variance. It's kind of up to you. Let me remind you that there's a nice relationship between the variance and the standard deviation. If you got the standard deviation, what do you have to do to find the variance? Square it. So there's two ways you can get the variance. One is I could just take this value and square it. So equals, click here, shift 6, and then the number 2, so you square it like that. Or you could simply type in var equals VAR, and that's really the only command. So, yeah, oh, there we go. Let's click those cells. Oops, there we go. Perfect. So the variance is just the square of the standard deviation, or vice versa. Square root of the variance is the standard deviation. Do try and keep track of those things. It will be something important for later. We don't use the variance as much because the units here are in some weird thing called dollars squared. And I don't even have an interpretation for dollars squared. At least inches squared I can think of as area. But yeah, the variance here, it does still represent some variability, but standard deviation is going to be more typical in terms of what you're going to look at. One more example like this from the homework. Listed below are the number of unprovoked shark attacks worldwide for the last several years. What extremely important characteristic of the data is not considered when finding the measures of variation? So let's start by finding the measures of variation, and then we'll think about this one a little bit further. You can do the mean, standard deviation, and the variance. So let's find all three of those. Average. And standard deviation. You guys getting the same numbers? 76.4.
Yeah.
Variance 11.5 squared should be 131-ish, 132-ish. So let's see, equals, and I'll just do it this way, var, click and drag, get all these. Yeah, 132.7. Okay. But if you're trying to decide, you know, do you want to go in the water or not, there's a piece of information that's kind of missing from all this. Does anyone know what else might be kind of good to consider as you're looking at this data? It's not really displayed by any nice summary statistics. It's not something that might be entirely obvious to you, especially the first time you go through a stat class. But how about if we plot it relative to time? So we can see, is there a trend? Is it getting worse? Is it getting better? Is it staying the same? What do you think? When you look at this graph, and all I did was I just plotted it. You can get that same graph on your Google Sheet just by clicking this last one over here for the chart. What do you think? Hermione? Is it staying the same? Is it going up? Is it going down? What do you think?
It's fluctuating.
It's fluctuating a little bit. All right. I mean, you got a low point here and a high point here. But other than a low point and a high point, which most data sets are going to have, it looks like it's bouncing around, you know, around the same kind of values for most of the data that we see here. You can do some other analysis, like a linear regression that we'll do later on. But, you know, a lot of it looks like it's, you know, more or less hanging around the same values. So, nice. All right. Any other comments or thoughts on that one? How about, let's see, so here. How about all these data sets? Are they going to be wildly different in terms of their means and standard deviations?
Yeah.
The interesting thing is, it's always a good idea to visualize your data because there could be certain patterns in your data that you're just not seeing. And what's unique about this set of data sets is called Datasaurus, is that all of these have the same mean, standard deviation, and correlation to the nearest hundredth as does this data set here, which is kind of funny, all right? Clever whoever came up with this, but visualizing your data is a good idea because there could be some patterns in your data that you just might not see otherwise. So I would recommend it. Let's see. There's a little bit more on your handout that I want to go through. So let me go back to that. Right here. Towards the bottom, you see some of the things that you should definitely know about your mean and standard deviation, or excuse me, about your standard deviation. We've gone through a few of these. It's always greater than or equal to 0. The values increase the amount of variability. There's something called the coefficient of variation, and it's a way to compare things from one data set to the next. So if you want to see how wild something is compared to the rest of the data, you can calculate the coefficient of variation. Basically, it's comparing the standard deviation to the mean and then turning that into a percentage. So let's look back with our first data set. That's this one over here. and we can calculate the coefficient of variation for both of these data sets. So we had these two standard deviations. So let me get rid of that. I'm just going to move you down one. Oops. Copy and paste. Let's do 3. All right. So we've got these two standard deviations here and here. If I wanted to calculate the coefficient of variation, what it's going to do is it's going to compare the amount of variation with this standard deviation compared to the mean. So equals, let's click the standard deviation divided by the mean. The mean in this case was 73, and then times 100. So in this case, the standard deviation is about 2.5, a little bit more than 2.5% of the mean. Whereas over here equals, and then this divided by the mean again, which was 73 for both data sets, times by 100. This was 2% of the mean. So it's reflecting what we would expect, that there's more variability in the second data set than the first one. Coefficient of variation. Nice. Continue and move down here. The last thing we need to cover on this side of the sheet is something called the empirical rule. That applies to data sets that look like this. What kind of a shape is this? Bell shape, normal shape. Bonus points if you said Gaussian, but we're not really going to use that in this class. But, all right. If you have normally shaped data, and that's what you're assuming if you're using the empirical rule, then within one standard deviation away from the mean, you have 68% of your data. That's a lot. Most of the data is in the middle if you have a normally distributed data set. If you move out to 2 standard deviations away from the mean, wow. Now you've got 95% of your data is within 2 standard deviations away from the mean. The thing about the empirical rule is that you're assuming that your data has a bell-shaped curve. So let's kind of underline that a little bit for ourselves in our notes. Bell-shaped curve, normally distributed data, etc. So that's a requirement of the empirical rule. And last but not least, suppose you move 3 standard deviations away from the mean. That is, take the mean, add 3 standard deviations, or subtract 3 standard deviations, you're going to get this spread. Fully 99.7% of your data is going to be within 3 standard deviations away from the mean. That's a lot. Now, it's rare that you're going to get stuff 3 standard deviations away from the mean or farther in a data set. Typically, maybe you get a couple values that are like 2 standard deviations away from their mean. If you counted here, how many standard deviations is there difference between the bottom and the top here? How many standard deviations is that? One, 2 to the left, and 2 to the right. Help me out here. How many is that? 4. All right, thank you. 4. So that range, or that distance here, is an approximation to the range. And if you wanted to or needed to, you can get an approximation to the standard deviation by taking the range and dividing it by 4. Because that's roughly, for bell-shaped data, that's what it's going to be. It doesn't always work perfect. It's going to depend on the data. But a lot of times it's a rough, crude estimate in the absence of anything else of what the standard deviation is. All right. Let's keep going with standard deviation. On the back of your handout is Chebyshev's rule. Chebyshev was a Russian mathematician. I've seen his name spelled like 3 different ways, including with a T out in front. Rumor has it that Chebyshev didn't know how to spell his own name. I tend to believe that, based on the variety of things I've seen. Now, Chebyshev's rule is again going to talk about how much of the data you expect to be within so many standard deviations away from the mean. There are a couple significant differences between Chebyshev's rule and the empirical rule. What's one thing that we required of the empirical rule?
It has to be a bell shape.
Has to be a bell shape. One of the big differences between Chebyshev's rule and the empirical rule is that Chebyshev's rule works for any data set. So underline that. It also doesn't tell you exactly how many standard deviations or how much data is going to be within so many standard deviations away from mean. It gives you an approximation. It says at least this percentage of the data has to lie within k standard deviations away from the mean. Now with the empirical rule, you could only let k be 1, 2, or 3. You didn't have any choice. Here, k can be anything greater than 1. So, okay, let's see. Let's see what happens here. Let's do it with a nice warm and fuzzy example to start with, which would be k equal 2. What if you wanted to find the minimum percentage of data to be within 2 standard deviations away from the mean? So that's going to mean plugging in k equal 2, 1 minus 1 over 2 squared times 100%. So I want to type that 2 in like this, 2 squared. To highlight, that's what we're putting in, is that k equal 2. Now, you don't have to do this in your head. You can do it on a calculator. You can do it on Google Sheets. 1 minus 1 over 2 squared is 1/4. 1 minus 1/4 is 3/4. 3/4 of 100% is 75%. Now, if you do that in your head, or if you do that on a calculator, that's fine. But what Chebyshev's rule is saying is that in any data set, at least 75% of your data has to be within 2 standard deviations away from the mean. At least that much. Could be more, could be a lot more, but at least 75% of your data has to be within 2 standard deviations away from the mean. Let's try that with another value. Maybe something that we can't do in our heads. Let's do k equal 2.5. Let's see what happens here. Okay, well this one, maybe I'll do this one on a calculator. So I don't feel like doing this one in my head. 1 minus 1 over 2.5 squared times 100%. Let's put in that 2.5 squared. And this one I'll just do, yeah, like I said, you can do it on your calculator or Google Sheets. Since Google Sheets happens to be open for me, that's pretty handy, I'll do it here, equals, parenthesis, 1 minus 1 divided by 2.5, shift 6, and then the square, times 100, and that should do it for me. It's going to be somewhere between 75% and 89%, I don't know where. 84%. Is that what you guys are getting? Sweet. Thanks for reminding. All right, so 84% of your data. Not bad, not bad. And if you did 3, you'd find about 89% of your data, etc. So Chebyshev's rule is kind of nice. Helps you figure out what percentage of data, no matter what, should be within so many standard deviations away from the mean. Let's talk about that relative to a human superstar, Marilyn Vos Savin. Marilyn Vos Savin's supposed to have the highest IQ of any human being living on the planet, 228. Now, for comparison's sake, the average IQ is supposed to be 100 with a standard deviation of 15. So, wow, that puts her way out there. Let's do a little bit of math on that. So, wrong one. Here we go. Come on, last chance. There we go. So if we had X was 228 and the mean was 100, then the difference between these two, X minus the mean, would be 128. And then if I divide by the standard deviation, divide by 15, that's going to give me 6 and 8 over 15. Let's call it 6.5. I know it's a little bit, 8/15 is a little bit more than 6.5, but we'll call it 6.5. So let's just see how unusual Marilyn Vos Savin is compared to most people. Now, of course, this is in any data set. If you're dealing with the empirical rule, which doesn't exactly apply here yet, you get a much better estimate. So times 100, you don't actually have to hit the times key here. So yeah, that says she's smarter than about 99.6%, or I mean 97.6% of the data should be within 6.5 standard deviations away from the mean. That's a minimum though. That's a minimum percentage. Keeping in mind that the empirical rule applies for normal data. Try and imagine just how few people would be 6 standard deviations away from the mean. 3 standard deviations away from the mean already has 99.7% of all the data. If you go 6.5 out, there's not going to be anything left out there. That's pretty outstanding. So, okay, comments or thoughts on anything to wrap up standard deviation? What's the big thing that I asked you to know about standard deviation? What's standard deviation tell you about some data? Don't let me down, come on.
Average spread.
The average spread of the data from the mean. And what else?
Spread increases, the deviation increases more.
Yes. As you increase the spread, so does the increase. It's accompanied by an increase in the standard deviation. Standard deviation is at least 0 and is more likely than not to be positive. The only time it's 0 is if all the data is the same. Nice, nice.